To examine the combined effect that more than one independent variable has on a quantitative dependent variable, we would use multiple regression. Our goal is to choose the best combination of independent variables. However, some independent variables work well together and some do not. Sometimes independent variables interact with one another, which is something we try to avoid. And as we've seen, some independent variables are just statistically insignificant and don't serve as good predictors of our dependent variable. In any case, the regression model assumptions still get checked, as well as regression outliers. As a quantitative method, the data that we use for multiple regression is most often quantitative. However, indicator variables may also be used. Indicator variables are created from our categorical independent variables, also known as binary variables because the coding is frequently in zeros and ones. We can create up to k-1 indicator variables for any single categorical IV, where k is simply the number of categories in our variable. Below in our data, we can see that we have three indicator variables: gender, ed level, and marital status. We could have made two indicator variables for each ed level and marital status because each of those have three categories. However, here, single indicator variables were made for all three. Once our data are prepared for multiple regression analysis, we begin by looking at a combination of independent variables and checking for significance. We get two types of significance results. First, we see the individual variable significance in our familiar t-test. But we can also run the f-test, which is based on our ANOVA model, to test the overall significance of our regression model. So here, on this model, which variables are insignificant according to the t-test, and which has the greatest p-value? It's notable that the t-test shows significance for individual variables. However, they only show that significance in the particular combination being considered. So we can see here that in this combination of 5 independent variables, gender, ed level, and age are statistically insignificant. And of these, age is the least helpful. Let's go to our Excel tool now to practice using our multiple regression tool. First, let's have a look at the data. We have the independent variables income, household size, and age that are quantitative. Gender, education level, and marital status are categorical independent variables that have been recoded into that binary format to make what we call an indicator variable. Now we can look at some combination of independent variables to see how that combination helps us to explain the variability in spending, our dependent variable. So let's begin with variables 1, 2, 4, 5, and 6, all as independent variables, and our dependent variable, always quantitative, is amount charged. The Worksheet tab Multiple simply shows us the data that we have selected, and that's it. This is important because as we look for the best combination of variables, we're frequently making changes to that combination, and we can check to see that we've selected what we want on this worksheet. On the Worksheet tab Inference 2, we can see our significance results. Our t-tests show that gender, ed level, and age are statistically insignificant in this combination of independent variables. But we could also see from our f-test in our ANOVA model that f for 5, 103 degrees of freedom is a very strong 82.65 with a p-value close to 0. So clearly something in our combination of independent variables is having a significant effect on our dependent variable and therefore what we want. We have seen that R squared is an important measure of effect size when using regression analysis. However, when using multiple regression, that is, at least two independent variables, adjusted R squared is always used. And this is because as we add independent variables to our model, R squared tends to increase. Adjusted R squared corrects or adjusts for this increase due only to the number of independent variables on our model. Below, we could see by the adjusted R squared statistic that this model, the combination of independent variables, in other words, explains about 79% of the variability in amount charged. But we also saw that not all of the independent variables are significant, so not all should be used. Removing an insignificant independent variable should have little effect on the adjusted R squared value. Collinearity concerns the correlation among independent variables. As we select the best combination of independent variables, it's best to have limited interaction among the independent variables. And in general, it's desirable for each independent variable to contribute uniquely to explaining changes in our dependent variable. However, this is challenging because, as we've seen in our data, each cardholder has several demographic variables. They all refer to the same cardholder. So it's very normal for some of those characteristics or measurements to interact. We can measure collinearity on a correlation matrix by checking the correlations among our independent variables. When correlation between the independent variables is strong, generally beyond 0.7, either positive or negative, we would decide to remove one of those independent variables. Below, we could see the correlation matrix, and we note that age and income are highly correlated, with a correlation coefficient of R equals 0.912. Therefore, we would make a decision to remove either age or income from our multiple regression model. A very popular method for helping us select the best combination of independent variables is known as the stepwise method of multiple regression. And stepwise could either be run forward or backward. The backward stepwise regression method is a process of systematically removing insignificant variables in steps, beginning with the least significant independent variable. Here, age has the greatest p-value, as we've noted. So using the stepwise method, we would remove age and refit the model. In other words, rerun the regression, only now without age. Then we would find the next least significant variable, and so on, until all of the p-values for our t-tests were less than 5%. Sometimes the resulting model, with all of those p-values less than 5%, is referred to as the corrected model. Let's return to our multiple regression tool and discuss our results. As we've noted, the adjusted R squared for our multiple regression is a little bit more than 79%, and therefore this combination of independent variables can explain about 79% of the variability in our dependent variable, which is amount charged. But we've also seen that not all of our independent variables contribute significantly to that 79%. Age, ed level, and gender all have p-values well beyond the required 5% for statistical significance. However, income and household size have p-values near zero. Therefore, much of this, nearly all of our 79% of explained variability, we would suspect comes from income and household size, making gender, ed level, and age unnecessary. So we've seen previously that age alone is a highly significant predictor of spending. We've used it for simple linear regression and gotten very strong results. So why is it not working here? As we've noted, age and income are highly correlated. So all of the explanatory power that we would get from age, we already get from income, and therefore age is not a significant variable on this model. We would say that age and income are collinear. Using our stepwise method, we would remove the insignificant variables in steps beginning with age. Going back to our data sheet, if we remove variable number 6, now we have 1, 2, 4, and 5. Let's check our data sheet. 1, 2, 4, and 5. That's what we want to run next. Let's look at our results. 79% holds. Remember, removing an insignificant variable should have very little effect on our adjusted R-squared. We've also removed that collinearity. However, we still have gender and education level that are statistically insignificant. Our next step using the stepwise method would be to remove ed level. And recheck our results. Our 79% is holding, however, we still have one insignificant variable, gender. So our final step would be to remove it. So we could have removed all of these at once, but we removed them in steps using our stepwise method because it is possible that removing one insignificant variable will help another variable become statistically significant. Here that didn't happen, but as we can see, we maintain our 79% of explained variability. Once we have the best combination of independent variables, we can use our familiar prediction and confidence intervals to make forecasts using our regression model. Multiple regression model building generally has the goal of making forecasts, and choosing the best combination of independent variables usually helps make our forecasts better. Below you can see that when we use a value of 125 for income, and 3 for household size, our y-hat value from our regression equation is $3,850.54. Our Excel tool will calculate the appropriate margin of error for both our prediction and confidence interval forecasts. Let's return to our regression results and practice using our regression forecasting intervals. First, let's review our model. We have a fully corrected model with only income and household size, and both of those have p-values very close to 0. The model overall has a very strong f-statistic, again with a p-value very close to 0. Our regression equation explains about 79% of the variability in amount charged, and there's no problem with collinearity. Remember, we're looking for strong correlations beyond 0.7. So this is a very good model for making forecasts for spending given cardholder income and household size. Simply by inputting the income of 125 and the household size of 3, we can see our y-hat value of $3,850.54. We would say that we're 95% confident that a single cardholder, a particular cardholder in other words, with an income of 125 and a household size of 3 should spend in the range $29.72 up to $47.29. On average, however, we're 95% confident that average spending for all cardholders who report an income of 125 and a household size of 3 should be in the much narrower range, $37.62 and about 70 cents, up to $39.38 and about 38 cents.